Hello, this is Mr. P, and today we're going to learn about logarithms. Logarithms can be a very easy topic once you understand what they really mean. For example, to calculate these three logarithms, once you understand the meaning, you should really be able to do all three of them in your head in less than 10 seconds, let's say. So taking a look at these, maybe you know them already, maybe you don't, but we will come back to these once we learn exactly what a logarithm is. So let's take a look at the definition. The definition of a logarithm, and we're gonna say that a is going to be a real number that is positive but not equal to 1. If you'll remember, this was the same restriction for the base of the exponential function. So a is positive and not equal to 1. Then the definition is log base a of x is equal to y if and only if, that's not a typo, that actually stands for if and only if, a to the y equals x. And there are two key observations to make that are going to solidify this understanding. First of all, if we look at y in the right side, then we see that y itself is an exponent. And if we look at it on the left side, y is equal to the logarithm expression. So on the left side, it's also a logarithm. And that's our first main key understanding here. Our first observation is that a logarithm is an exponent. So if you understand that a logarithm is an exponent, then we can read this sentence with a little more understanding. We can say that the exponent, because a logarithm is an exponent, so the exponent of a that gives you x is y. Now notice how y is the exponent of a, and the result is x. So the exponent of a that gives you x is y. And that would be our second observation. We can literally read those as the exponent of a that gives you x is y. And that way you can go back and forth from logarithmic form to exponential form. Both of these statements are equivalent. Just the left one here is in logarithmic form, and this one is in exponential form. So you should be able to go back and forth from this one to the logarithm or from the log to the exponent, because a logarithm is an exponent. All right, now let's look at those log problems we started out with again. And let me give you a couple of seconds. Go ahead and try to figure those out yourselves. Okay, hopefully by now you should have realized that the first one is the exponent of 2 that gives you 8. So in your mind, you should be thinking 2 to what power gives me 8? The exponent of 2 that gives me 8, this is what we're looking for. Well, that would be 3, because 2 cubed is 8. So the exponent of 3 that gives you 9, well, hopefully you realize that that would be 2, because 3 squared equals 9. 3 to what power gives me 9? Well, 3 to the second power gives you 9. And then even something like this, which would normally stump some people, you can say the exponent of x that gives you x cubed. Well, of course, that would be 3. Because in your mind, you're saying x to what power gives me x cubed. So like I said, these can be very simple concepts if you understand what the notation really means. A logarithm is an exponent. So here we're looking for the exponent of x that gives you x cubed. All right, now looking at logarithm as a function, we're going to talk about the graph of that function and the parent function. That was going to be one of our parent functions. So f of x is log base a of x. And again, notice this only applies when a is positive and not equal to 1. Same exact restriction we had for the exponential function. And for the properties, I do want you to key in here that this is the opposite of the exponential function. Or more accurately, it's the inverse function of the exponential function. So if we look at the properties, again, we have f of x is log base a of x, where a is greater than 1. We're going to look at the one where we're dealing with a being greater than 1. So here we have the domain is going to be from 0 to infinity, because as far as an input value for x, and this is called the argument of the logarithm. What you're taking the log of is the argument. Your argument must be positive, and so you can't take the logarithm of a negative number. Matter of fact, you also can't take the logarithm of 0. So up till now, our restrictions for domains have been can't divide by 0, you can't take the square root of a negative number. Well, now here's another one, is you cannot take the logarithm of a non-positive number. So our domain is 0 to infinity, which is just the positive numbers. The range, however, will be from negative infinity to positive infinity. And if we actually look at the graph, this is the graph of log base a of x, and or just log, and with different bases, we'll just change the slope at which it goes through that intercept, just like it did for the exponential function. But basically, your logarithmic curve is going to look like this. And notice how the range, which would be the y value, starts out at negative infinity and keeps going up to positive infinity. Yet the graph itself only exists to the right of the y-axis. In other words, from 0 to infinity, not including the endpoints. Now the intercept is 1, 0, does have an x-intercept with no y-intercept. And it's increasing over its entire domain. So as it goes from left to right, it's always going up. And then one way we could say the asymptote here, there's a vertical asymptote at x equals 0, which is the y-axis. And we can say that the function approaches negative infinity. So as you're going this way on the function, you're going to approach negative infinity as x approaches 0 from the right side. The little plus there means from the right side. You can't approach it from the left side because the graph doesn't exist to the left of the axis. Also, this is a continuous function, no holes in it. And here's the important one that goes back to it being the inverse of the exponential function. The graph itself is the reflection of that exponential function about the line y equals x. And if we remember from our Algebra 2, if you have the line y equals x, and you take a graph such as the exponential function and reflect it across that line, then you will have the graph of the inverse of that function. Because in effect, you are switching the roles of x and y by reflecting it across the line y equals x. So this is something that's going to be very important that we're going to be using later, is that the inverse of the exponential function is the logarithmic function. All right, let's look at a couple of special notations we're going to be using. One thing I almost forgot. When we look at, since these are inverse functions, then I do have to mention that the domain of the logarithmic function is the range of the exponential function, and vice versa. The range of the logarithmic function is the domain of the exponential function. That's something that also occurs because they are inverse functions. And we can see that from the properties here and combining them with the properties of our exponential functions. Okay, if we look at some special notation, there are two logarithms that have a special notation for them. First is log base e. E was that special number we learned about in exponential functions, and log base e is used so much in higher mathematics that in order to shorten it, it's written as simply ln, which stands for natural log. It was originally a French term, like log naturel. That's why it's ln rather than nl, but ln stands for natural log, and we read it as natural log. So the actual definition of natural log, since it's in base e, is y equals the natural log of x, if and only if x equals e to the y. So that is a very common function. If you want to see what the graph looks like with its slope, that would be y equals the natural log of x, and compare that with y equals e to the x, two very important functions in higher mathematics. Also in science, the common log has been used a lot. When we look at the common log, that is base 10. Even though it's called the common log, we don't actually use it that much anymore. Natural log is definitely used more than common log. But log base 10, rather than write the 10, it has adopted the notation just log. So for any other base, it would have a number written down there. That's why we had the a in the previous examples. But if your log doesn't have a number written as a base, then it's assumed to be base 10. And of course, its definition is right along the lines of all the others. It's y equals log x if and only if x equals 10 to the y, because 10 is the base. And just for a comparison, this is what the graph would look like for 10 to the x would be the exponential function, and natural log, the common log, sorry, of x would be this one. Notice how with the exponentials you have a steeper slope through the intercept when your base is larger, and you have a flatter slope through your intercept for the logarithm when your base is larger. So again, this one is e to the x, this one is 10 to the x. So we have natural log and common log. All right, let's look at some problems. Sink our teeth into some problems here. All right, first of all, we have to be able to find the domains of logarithmic functions. So the key idea here is that you are not allowed to take the log of a negative number or of 0. So your argument, which is what's in the parenthesis here, your argument must be positive. So this solution is pretty straightforward. Our domain will be all values of x for which the argument here is positive, and greater than 0 means positive. So to reiterate, the argument must be positive. So x plus 3, which is the argument, is greater than 0. And then subtract 3 from both sides. You get x is greater than negative 3. Or in interval notation, you have the interval from negative 3 to infinity. So that would be our domain for this function. Likewise, with b, we have log base 5, and it actually doesn't matter what the base is, you still can't take the log of a negative number. So now we have the inequality that this rational function, it's inside the parentheses there, has to be greater than 0. And as a little reminder of your Algebra 2, when you're solving a rational inequality like this, you're going to take a number line and break up the number line using the critical values that are zeros of the numerator and zeros of the denominator. So negative 1 causes the numerator to be 0, positive 1 causes the denominator to be 0. We plot those points on a number line, and that breaks our number line up into 3 distinct intervals. Then we can pick any number inside that interval as a test point. For example, for this interval, if I take negative something very large, negative 1 million, for example, then here the top will be negative, and the bottom, subtracting a negative, is going to be plus, so the bottom will be positive. So a negative over a positive is going to be a negative. And that means everything in that interval is going to be negative. If I pick a number inside of the interval, remember you can't pick the endpoints themselves, you have to pick a number inside, such as 0. If I pick x to be 0, this goes away, 1 over 1 is positive. And if I pick a very large number, then my numerator will be positive, my denominator will be negative, and a positive over negative is a negative. So these are our 3 intervals, and the only place where it is greater than 0, in other words where it's positive, would be between negative 1 and 1. So that's how we find our domain. Our domain is going to be all values between negative 1 and 1. We can say it using inequality notation, or you could say it using interval notation. The interval from negative 1 to 1, not including the endpoints. And not including the endpoints because we can't take the log of 0 either. It must be positive. All right, looking at the final one, we have log base 1/2 of the absolute value of x. And you might be thinking to yourself, well, that should be any number, because no matter what you plug in, you're always going to get back something positive. Well, not quite. If you plug in any negative number, you'll get back something positive. If you plug in a positive number, you'll get back something positive. But if you put in 0, then you're just going to get back 0, because the absolute value of 0 is 0. So officially, though, taking the absolute value of x and setting that to be greater than 0, that will always be true provided that x does not equal 0. So really, our solution here for the domain is going to be all real numbers except x equal to 0. And by interval notations, we would write that as negative infinity to 0, unioned with, I would have used the union symbol here, but unioned with 0 to infinity. So that's all real numbers except 0. All right, now let's let you try one. And go ahead and pause the tape. Go ahead and try to find the domain of this function. And I'll give you a moment to do that. Okay, hopefully you've got this problem done. And looking at this, we want to, of course, set the argument to be greater than 0, which means we need to look at intervals here. We're going to take the number line itself, and we're going to put the critical values. We're going to plot the critical values, which will be -1 for the numerator and 0 for the denominator. So plotting -1 and 0, I'm going to look at the leftmost interval and think to myself, well, a very large negative number, if I put it in the top, it's still a large negative number. And if I put it in the bottom, it's going to be a large negative number. So negative over negative is going to be a positive. Now, if I look at something between -1 and 0, like -1/2, -1/2 plus 1 is going to be positive. I don't care what the numbers actually is, I just know it's positive. And -1/2 in the denominator is negative, so positive over negative makes a negative. And then any large positive number, I'm going to, of course, get a positive over a positive, which gives me a positive. So that means I want, since I'm looking for only values where the argument will be greater than 0, I want these two positive intervals. And in interval notation, that would be the interval from -infinity to 1, union with the interval from 0 to infinity, not including the endpoints, because you cannot take the log of 0. All right, another thing we need to be able to do with logarithms is transformations. Now let's start with this equation. We want to graph the negative of the natural log of x plus 2. And the first thing we're going to do is think about our parent function. So the graph of our parent function, which is just simply the natural log of x, this is what that graph would look like. And notice how it does have some points in here. They are being they're definitely being rounded, but that's approximately what that graph would look like. Now we have two transformations. We have multiplying by a negative outside, and we have adding to inside the parent function. So we can take them in any order we want, but let's start with the negative. Multiplying by a -1 outside means we're going to reflect it about the x-axis. In other words, we're going to reflect it vertically. So every point will be reflected about the x-axis. So this point here will become a point down here. This point here will become a point down here. This point actually stays where it is. And then this point down here will reflect to become a point up there. So we're going to spin it around, and it will look like this when you reflect those points. So this is now the equation y equals negative natural log of x, a reflection about the x-axis. And then the next transformation, or the final transformation, is we're going to replace x by x plus 2, which is the same as adding 2 to the inside. Now, if you ever forget whether you go left or right, because any changes inside result in horizontal changes, any changes outside were vertical, as we saw in the reflection. But if you forget whether you add or subtract, you can just realize that the value of x that causes that parenthesis to be 0, will be -2. So that the asymptote, which would have been when you're taking the natural log of 0, that asymptote, instead of being at a 0, is now going to be at a -2, because that's the value of x. So this actually represents a shift to the left. So when we do that, that asymptote, which used to be the x-axis, I'm sorry, the y-axis, and you don't actually have to draw it when it is the y-axis itself, but once you shift it, now you definitely are going to have to draw that vertical asymptote. So basically, we're taking this graph, and every point we're just shifting 2 units to the left. So that means we're only affecting the x values. Notice how 1/2, when I shift 2 units to the left, becomes -3/2. +1 shifted becomes -1. We have a +2 shifted becomes 0, and 3 when you shift it 2 to the left becomes 1. The y values all stay the same. All right, so doing the 2 transformations, we start with our parent function, transform it by reflecting, and then shifting. All right, let's take this one step further and see if you can recognize this shift. Notice how this is, the function is the natural log of x plus 4. And if we looked at it in the calculator using these settings for our window, then the question is which one of these would be the correct graph. Well, the way to think about this is the natural log of just x, that would be something that would come up like this and out where it would approach the y-axis as its asymptote. So approaching that y-axis as its asymptote, we're going to shift this in some direction. Now, since we're making a change inside, we're going to shift it left to right. And the easiest way to think of it is that point that was at 0, that vertical asymptote that was at 0, will now become a -4 because that is the value of x that causes the inside to be 0. So that's really a shift 4 units to the left, but we're not reflecting, so it's not going to be D, it's actually going to be A. Because what would have been this graph, if we shift 4 units to the left, will now become this graph. So the correct one here was A, should have been the correct shift. So if you ever get confused whether adding or subtracting goes left or right because it's the opposite of your intuition, just ask yourself, what is the value of x that causes that to be 0? And whatever property that was, usually in quadratics or something, that would be the vertex. But here, the value of x that causes it to be 0, that's going to tell you where that asymptote is, where that vertical asymptote is. And that vertical asymptote in this case would be at -4, which the calculator doesn't actually draw the asymptotes. All right, let's look at some properties of logarithms. And these basically go along with your properties of exponents, or laws of exponents, that we looked in the last section. The first 2 are pretty useful. We're actually going to show a proof of these later, of these first 2. But the first one says log base a of 1 is 0, and that is because a to the 0 is 1. Also, log base a of a is 1 because a to the 1 is a. So we have the logarithmic form and the exponential form, but I'm still going to show a proof of both of these in a little bit. Now the third one's called the inverse property. That says log base a of a to the x means that these 2 can cancel, and it just leaves the x. Likewise, if you have a to the log base a, then these 2 can cancel, and again it leaves just x. Those are called the inverse properties. We'll be using those a lot when we're solving logarithmic equations. So logarithms undo exponents, and exponentiation undoes logarithms. And the one-to-one property says if you have log base a of something and log base a of something else, the only way those 2 are going to be equal is if those somethings are equal. So log base a of an argument equals log base a of another argument, then those 2 arguments must be equal. The logs can basically cancel out on both sides. All right, so let's look at some examples here. The first 2 we're going to solve for the variable, and the second 2 we're simply going to simplify. Now the first one we have, and I'm just going to rewrite it here for a little clarity. You have log base 2 of x equals log base 2 of 3. Well, this is going to be that one-to-one property where we have the log of the same base on both sides. And when that happens, you can just cancel out both sides, and that'll leave you simply with the fact that x equals 3. With B, we have basically another one of our cancellation ideas. this one is actually the second property. We have log base 4 of 4. Notice we're taking the log of a base that's the same as our argument. So whenever that happens, those two cancel out and become 1, just like this property says. So therefore, since that's all equal to x, then x is just equal to 1. All right, for C, we have log base 5 of 5 to the x. And that is going to be your inverse property. That is this one here with a being 5. So it doesn't matter what the numbers are. If these two are the same, then the log and the exponentiation, they cancel each other out, leaving just x, which is our simplified version. And then finally for D, we're going to simplify 7 to the log base 7 of 14. And again, since this number and this number are the same, these two can cancel out. That's only when they're the same, by the way. And when those cancel out, they go away, and all you're left with is the 14. Now with natural logs, they have the exact same properties. We're going to take a look at those, although they are exactly the same. Natural log of 1 is 0, just like log base a of 1 is going to be 0. Just in this case, your a is e. So really, if you go back to any of these properties and you change the a to an e and then rewrite it as ln rather than log base e, then you will still get these exact same properties. But these are the ones you'll probably be using the most when you get up into calculus. So log base e equals 1, natural log of e equals 1. The natural log of e to the x, those cancel out, leaving just x. And e to the natural log of x, again, those cancel out, just leaving x. Those are your inverse properties. And the same thing with the 1-to-1. If you have natural log of x equals natural log of y, that can only happen if x equals y, if the arguments are the same. All right, so let's try some of these examples. And sometimes you'll need to do a little bit of rewriting, a little bit of algebra, so that you can make it like one of these properties. For example, on the first one, for a, that form doesn't really help you too much. But you can rewrite 1 over e as e to the negative 1. And now you have the natural log of e. Now you have that cancellation, which happens right there. And you get just negative 1. That was eventually using the inverse property. For part B, we have e to the natural log of 5. And then this is, again, our inverse property. E and the natural log cancel each other out, and it leaves just a 5. For C, we have 4 natural log of 1. Well, because of property 1, the natural log of 1 is 0. So we can make that cancellation to be 0. So it's really 4 times 0, which is just 0. And then for D, we have 2 times the natural log of e. While using the second property, we see that the natural log of e is 1. These are ones you're going to have to memorize. And therefore, 2 times 1 is simply 2. So we will need to be able to do a little bit of algebraic manipulation using logarithms and exponents. But with a little practice, that should come pretty naturally. All right, for that proof that I promised you, we're going to go ahead and prove both of those first two properties. We're going to start in the most generic, which is log base a. So later on, if we choose a to be the special number e, then this would also apply for natural logs as well. So log base a of 1 equals 0. All right, so what I'm going to do here is I'm first going to let x equal log base a of 1. So I'm going to set x to equal the expression on the left. And then I want to rewrite it in exponential form. Notice how we have x is the exponent of a that gives you 1. So I'm going to rewrite it as such. X being the exponent of a, that gives you 1. From here, I'm going to realize that 1 is the same as a to the 0. So I'm rewriting both sides with the same base. Since a to the 0 is 1, I can rewrite the expression or the equation like that. And next, I'm going to use that property that says if the bases are the same, then the exponents must be the same. And that is simply going to mean that x is equal to 0. And since we said x itself was that logarithmic expression, now I can back substitute and say, therefore, log base a of 1 equals 0, because log base a of 1 was x itself. And the next proof is actually almost exactly the same strategy. First, I'm going to let x equal this expression on the left. So let x equal log base a of a. And now I'm going to rewrite this in exponential form, because x is the exponent of a. That gives you a. So x is the exponent of a. That gives you a. Rewriting both sides, I'm simply going to write a as a to the first, which they are equivalent. And then since our bases are the same, that means the exponents must be the same, so x equals 1. But we said x was this expression to begin with, so I can say, therefore, log base a of a equals 1. And a lot of times you'll see proofs will end with quod erat demonstratum, which is Latin for that which was to be shown, or that which was to be demonstrated. But most mathematicians like to say it was quite easily done. And that's the end of our logarithmic discussion, and enjoy.